Let's see how feedback helps in the reduction in frequency distortion. The effective gain after feedback is AF is 1 by A by 1 plus beta A. And this is equal to A by beta A. If beta A is very much greater than 1, then you can approximate AF to be equal to 1 by beta. So if the feedback network is purely resistive, the gain with feedback is not depending on frequency. You can see it is depending on beta only. If this beta is, if this network is purely resistive, then there is no dependence on frequency. So even if the basic amplifier with gain A is dependent on frequency, with the feedback you can make it independent of frequency. So practically the frequency distortion arising because of varying amplifier gain with frequency is considerably reduced in a negative voltage feedback amplifier circuit. Now let us see what happens to noise and nonlinear distortion. Signal feedback tends to hold down the amount of noise signal and nonlinear distortion. So it is going to reduce it. The factor 1 plus beta A reduces both input noise and nonlinear distortion for considerable improvement. But this 1 plus beta A is causing a reduction in the overall gain. We know that it is causing a reduction in overall gain. At the same time, it is reducing both input noise and it's resulting nonlinear distortion. So if we are using additional stages to bring overall gain up, so some stages if you use after this to bring the overall gain up, then these extra stages may also introduce noise back into the system. So how to solve this issue? That is by readjusting the gain of the feedback amplifier to obtain a higher gain while also providing reduced noise signal. So there has to be an adjustment between the feedback as well as the forward gain of the amplifier. The next is the effect of negative feedback on gain and bandwidth. Again, we are coming across the same expression. AF is equal to A by 1 plus beta A. And that is equal to 1 by beta for beta greater than A. So for a practical amplifier, the open loop gain drops off at high frequencies. You know that due to the active device and circuit capacitances. So gain may also drop off at low frequencies. This is it. The drop in gain at high frequency and low frequency. So once the open loop gain drops low enough, the factor beta A is no longer much greater than 1. So AF is equal to 1 by beta does not hold true when A drops very low. So here you see this is the gain A and this AF is the gain with feedback. So when the gain was A, the bandwidth was B. But when the gain has reduced to AF with feedback, the bandwidth has increased to maintain the gain bandwidth product constant. Okay. So what is happening with feedback? The gain has reduced. Okay. But the bandwidth has improved. So this is the effect of negative feedback on gain and bandwidth. Then what happens to the stability of gain with feedback? So how stable the feedback amplifier is, how stable it is compared to an amplifier without feedback. That is what we are going to see. So with feedback, if you differentiate and see DAF by F, both left hand side and right hand side, if you differentiate, you see DAF by AF is equal to 1 by 1 plus beta A dA by A. For beta A greater than 1, then this term will be 1 by beta A dA by A. What does this show? The magnitude of the relative change in DAF by AF is reduced by a factor beta A. See, this change in DAF by AF is reduced by a factor beta A compared to without feedback. If it is without feedback, it is dA by A, and that factor is reduced by, that term is reduced by a factor beta A if you have feedback. So this is overall gain. The change in the gain or the stability is affected by a factor 1 by beta A, which means if there was no feedback, it would have been dA by A. With feedback, it is reduced by a factor beta A. So with this, we are stopping our discussion on feedback and its effects. Thank you.